again to one of our videos. Today we'll be looking at thermochemistry. Okay, thermochemistry. What is thermochemistry? Thermochemistry simply deals with what? Heat changes that is accompanying what? Chemical reactions or physical reactions. Okay, heat changes that accompanies chemical reactions. You know, when chemical reactions take place, heat is either evolved or absorbed. Okay, so you remember from your secondary school, you know about endothermic reactions and what? Exothermic reactions. Okay, I believe you can be able to differentiate between endothermic reaction and exothermic reaction. Exothermic reaction has to do with what? Heat that is what? Released, okay, from a chemical reaction. While endothermic reaction is talking about absorbing of what? Heat. So let me quickly just show you how we can represent these endothermic reactions and exothermic reactions graphically. Okay, so when you have something like this, we call this the energy profile diagram. Okay, so when you have your energy profile diagram, of course you know that if a reaction is starting from any point, this is the potential energy. Okay, this is the energy. This vertical axis represents the energy. Okay, while the horizontal axis represents what? The reaction coordinate. Okay, I can write it here for you. Reaction coordinate. Okay, why this is the what? Energy. Okay, so now if you have something like this, watch, have this. Now this is your reactant before the reaction. Okay, this is your reactant. Okay, so when the reactant reacts, it probably follows this curve and then gets to the what? The product. Okay, and for it to arrive at this product, it must get to what? It must overtake. It must be able to. It should be able to overcome this energy we call the activation energy, right? So while from here to here actually represents what? The heat that is either absorbed or given off. So for this particular graph now, you will notice that from the reaction coordinate, you see that the energy of the product is higher than the what? The reactant. Okay, the heat energy is greater than the what of the what? Product. So from the reactant, so we have that. We can simply say that since delta H, which is the enthalpy or the heat of reaction, the difference between the heat of reaction of the product and the reactant can be given as heat of product minus what? Heat of what? Reactant. Now look at this very well. You will notice that the heat from the product is greater than the heat of what? Reactant. So when this happens, the reaction or the process is an endothermic process. Okay, so this process represents an endothermic process. Okay, why? Because heat is absorbed. Okay, so and how do we know that heat is absorbed? Delta H will be positive. This delta H here will be positive. Okay, and it makes sense because if, for example, we take this particular place to be a certain number and we take this particular place here to be a certain number, you notice that, remember, as we go up here, energy increases. Okay, so you notice that the difference between y and x here will be what? A positive value. So for such a process like this, we say it's what? It's an endothermic what? Process. So studying these heat changes accompanying each of these processes is what we call thermochemistry. So this is for endothermic process. I could also show you for exothermic process. For exothermic process, the difference will just be in. Okay, so remember that for an endothermic process, the product is greater than the what? The reactant. But for exothermic, okay, for exothermic, the product will be less or the reactant will be greater. So if you have the reactant here, remember this energy I'm drawing here, what I'm drawing here is the required or the minimum energy that you must break or overcome for you to transition to the product. Okay, for you to transition to this product, you must overcome this energy we call the activation energy. Okay, so when you overcome this energy, then you get to this point. This point is called the activated complex. Okay, activated complex. So when you have arrived at this point, then you can fall back to the product to have this product here. So looking at this now, you will see that why this here, this one is the measurement of what? The heat, the change in heat of reaction. Okay, so the difference in the heat of reaction here, delta H for this reaction is still HP minus what? HR. And if you notice very well, for this particular condition, our HR is greater than what? Our HP. So whenever HR is greater than HP, or HP is less than what? HR, then we say that this reaction is an exothermic reaction. Now watch carefully and look at the difference between these two. Remember, this is still your activated complex, okay? Okay? Now, these heat changes giving rise to endothermic and exothermic process. When you try to study them and know how it comes about, how to calculate or quantify them, then you are actually studying what? Thermochemistry. So looking at these two diagrams, we call this the energy profile diagram. Remember, I can still call here energy. This is the reaction coordinates, right? This is the reaction coordinates. So now, these things that we have written on the board now are just theoretical ways of trying to deduce heat of reactions via endothermic and exothermic process. Now, these heat changes that we observe in chemical reactions, how can we measure it? We can actually measure these heat changes experimentally using an instrument we call the calorimeter. Now, for the sake of this class, we are going to be focusing on the bomb calorimeter and the flame calorimeter. Okay, the flame calorimeter. These are the two calorimeters we use to measure heat changes at several constant conditions. Okay, the bomb calorimeter measures heat changes at constant volume. Okay, at constant volume. Okay, so for the bomb calorimeter, how do we use this instrument to measure? Now, these instruments or these devices, they are used to measure the heat energy accompanying any chemical reaction with respect to a particular. For example, let's talk about mathematically, how can we use this to measure it? So from experiment, the mathematical expression can be given as heat, which is Q. Remember, when we talk about heat, Q represents heat. But when we talk about heat of reaction, we can also represent it with what? H, or enthalpy. So know the difference between H and Q. This one is enthalpy or heat of a reaction, but this is just heat, measurement of heat in and out of a system, of a thermodynamic system. So mathematically, we can measure this heat of a thermodynamic system by using this equation, MC change in theta, temperature. Okay, or you can say Q is equal to MC change in theta. Okay, where these two represents what? Change in what? Temperature. Okay, take note, this change in T is also T2 minus T1, or change in theta is equal to theta 2 minus theta 1. So if you know the temperature before and after the reaction, you can do the measurement. Okay, now this M represents the mass of the substance you are trying to measure the heat. Okay, so this is the mass. This M stands for the mass. Okay, I can just write it somewhere here. The M represents mass. Okay, now this C here represents the specific heat capacity of the material. Specific heat capacity of the material. Heat capacity of the material. Okay, So if we are using water, okay, for the calorimeter, you can use water, okay. So you measure the mass of the water and the specific heat capacity of the water, and then the temperature change before and after the reaction. So mathematically, we can actually measure heat capacity using this equation, okay. Now, talking about the calorimeter, I said something about bomb calorimeter and flame calorimeter. These two calorimeters are used to measure heat changes, okay, but they work with different conditions. So as time progresses, we'll talk about how we can be able to use this bomb and the flame calorimeter to measure these heat changes. Remember, the beginning of this study, we talked about thermochemistry. What is thermochemistry? We are trying to study heat changes that accompanies chemical reactions, okay. So, and these heat changes can either be heat from a reaction that is evolving or absorbing, okay. So, and if the reaction is an endothermic process, do you know how to represent endothermic process? Yes. Look at an endothermic process graphically. Look at an exothermic process graphically. So with this, how can we be able to calculate these heat changes? We'll talk about these things as time progresses in the video. So pay attention and watch. So now, these heat changes we have been talking about that accompany chemical reaction. Now, the chemical reactions we are going to focus, okay? The chemical reactions you have to know, or you have to look into, which I will not probably go detail, because if you go to the Learn Extra app, you look at the definition. You don't have to know too deep about it. Just know the heat changes that accompany such reactions. The reactions we are going to focus include, I know most of you have heard about those reactions. The reactions we'll focus will include combustion. I know you know what is combustion reaction. I'll quickly talk about it. Combustion. What's combustion reaction? This is a reaction between what? Something and what? Oxygen in excess. Oh, in excess, right? Okay, in excess is called a complete combustion, but when the oxygen is insufficient, it's called incomplete combustion. So take note, whenever oxygen is being reacted with something, then the reaction is called a combustion reaction. And now, the heat of reaction of every combustion reaction is negative, because for combustion reaction, there is always what? Releasing of what? Heat. So the enthalpy or the heat of reaction from combustion reactions are always negative. So you also go ahead and look at some heat also from neutralization reaction. Neutralization reaction, that is reaction between an acid and an alkali to form salt and water. When such a reaction happens, heat is either absorbed or produced depending on the reaction. So the next one we'll talk about is heat of atomization, okay, atomization, and also heat of hydration and heat of formation, and lastly heat of what? Solution. Okay, so when these reactions are taking place, heats are either evolved or absorbed. Okay, so these heat that are evolved or absorbed are known as its heat of what? Reaction. Okay, so now for this heat of reaction, we can also look at this heat of reaction as standard conditions. What are the standard conditions? The standard conditions for heat of reaction is that it must be happening at a specific temperature, which is 298 Kelvin, and also 1 mole of that substance is undertaking that reaction at a standard temperature of 298 Kelvin, okay, and a pressure of what? 1 atm. Okay, so these are the conditions needed for it to be a standard heat of reaction. So remember that these heats produced from this reaction are called heat of combustion, heat of neutralization, heat of atomization. But as standard condition, it is called standard heat of combustion, standard heat of neutralization, standard heat of atomization. Why is it standard? It is standard because it is undergoing such reaction at a standard state. But at a normal state, it is called heat of combustion. So these various, when you go into the app properly, you will now be able to see the definitions of all these things, and then you should be able to know the definition, because in exams, what you are likely to see is just to define this, okay? Just know the definition. There is no in detail, we're not going into deep calculation on all these things. We'll also see some of these things when we approach laws of thermochemistry, where we have Hare's law and the rest of them. So this is just a review of what thermochemistry deals with. So all these things now, we'll start taking them, some of them bit by bit, and discuss as the video progresses. Okay.